17.2 all the way through 19.2, but obviously only the ones you see listed. If you ever are in doubt as to what sections it's on, just look at the problem sets. You can see which ones you did, or just look at the notes to see which sections were omitted. For example, 18.2 and 18.3 aren't there, right? So 17.2, 17.3, 18.1. Let's group those together. There were similar ideas. And then 19.1 and 19.2 began a newer idea. What was the gist of 17.2, 17.3, 18.1? What were we looking at for those? Reese?
Charges of electrons and protons.
Yeah. And what else? What about those charges? It didn't have to just be those, but yeah. Charged particles in general. What about them?
Opposites attract.
Opposites attract. Electric fields are produced. What else? There's one other thing in 18.1 that we talked about. What was 18.1 all about? Yeah, electric potential energy. And that is a little bit tricky, so let's make sure we spend some time on that today. But there are three formulas. Let's look at all three together, because a lot of students get confused as to which to use on problems. The first one was the electric force. That's barely readable, right? How about blue? Any better? Should I just get rid of this template, green template instead or something? So the four formulas are very similar, right? And it can be confusing at times as to when to use each of them. So let me spend a few minutes just discussing what some things are that might help you as indicators, right? So when you look at word problems, you need to look for indicators. So for example, Elliot, if you saw the word newtons, what do you think right away? Force. So you're probably using one of the two formulas that have Fe in them. Agreed? Okay. So use your indicators. If you see joules, where do you think that's going?
Energy.
Potential energy. So probably in the bottom right quarter. If you see something with newtons per coulomb, what was newtons per coulomb? Which one's Mike?
E.
Yeah. E is dimensions of newtons per coulomb. E is the electric field intensity. Newtons per coulomb. So units are a good indicator. Next, if you hear the word source, there is a source generating an electric field. The source is Q. Let's draw an arrow and write that right here, please. This is the source. So if you hear that, oh, there's two protons at a certain distance from each other and stuff, it's the word source that's going to be an indicating factor for this. Okay, source. The R value is the distance from the source in this problem. The distance from the source. It is not the distance between two particles. It's the distance between poop particles. Between two particles for the first formula up here and the bottom right formula. For Fe and Pee, R is the distance between the two particles. Whereas the electric field, let's take a look at what that means. Get rid of this first. So an electric field might be like, ready? Here's a sphere with a charge of 3e on it. First of all, what is little e again?
1.6 times 10 to the negative.
That's it. Very good.
But
1
you
point.
multiply 3 by that rate to get that 12.
Exactly right. So the charge on this sphere that's a source, or it's generating an electric field, is triple the fundamental charge. So 1.6 times 10 to the negative 19, that is the fundamental charge. So if you multiply that by 3, you get the charge on this sphere. Hold that now, okay? Now, the sphere generates a charge. So this is the source that is drawn here. We are looking for the electric field strength, let's say, at a distance away from the source. Call that X. This is that gap R. Okay, that's when you're going to see the electric field problems. This electric field is a positive field, so it produces a field outward. And if you wanted to find out how strong that field was at a distance of, say, 5 centimeters, you start by labeling it that way. You know R, you know Q, which is triple the fundamental charge. You know Kc, that's a constant, always, 9 times 10 to the 9, the same thing every time. So you are trying to determine E. Or maybe you have E and you're determining R. Or you have E and R and you're determining the source. But any of those are possible. But remember that you're looking for the field at some given location.
What's the deal with the problems like where it was like...
Now a proton is placed there?
No, it was like when you ask how many electrons are in the thing, it was like we divide... It's something to do with...
Yeah, if you had like an overall charge on a particle and it says how many electrons are responsible for that charge or whatever, you divide by the charge per electron. What's the charge per electron?
What?
What's the charge per electron? Charge per electron? Yeah, so you divide by that quantity. So if I had a sphere that was like 20 coulombs of charge, you take 20 coulombs divided by 1.6 times 10 to the negative 19 coulombs per electron, giving you the number of electrons that make up that charge. Remember, realistically, every charge is a multiple of the fundamental constant E. But, we sometimes say things like 30 coulombs. It's probably not exactly 30 coulombs, right? Because, there's probably not an exact number of electrons that happen to add up to be exactly 30 coulombs. But we estimate when we give charges. But remember that all charges are really multiples of E. Okay? E.
How do you know what it's a proton or an electron?
Like this?
Yeah.
All right, so here you don't know. Here all you know is that there's a source providing a positive charge that is triple that of the elementary charge or elementary fundamental state. So this would be, what element is 3? Is it lithium or is it lithium? I know it's hydrogen, helium, lithium. So this would be like a lithium nucleus.
Okay, so...
If the test says a boron nucleus or a carbon nucleus or a hydrogen nucleus, then I'll tell you how many protons are in it. Okay? I'll say a hydrogen nucleus consisting of 5 protons and 5 neutrons exhibits a field around it. Well, right away, if it has 5 protons, the charge is 5e. If it has 8 protons, it's 8e.
Multiply by 1.6 or negative 1.6?
Positive 1.6, because it's a proton in that
that's
case.
what I was asking.
But if I said there's a clumping of 5 electrons in space, then it's 5 times negative 1.6 times 10 to the negative 19. Okay? If you were to, say, calculate the electric field, okay? Say you calculated this E value right here that I'm flashing toward. Okay, you calculated E, and you found out that it was like 20 newtons per coulomb, okay? And then I said, what kind or what force would a proton feel at this location right here? Because originally there's no charge here, right? It's just a point in space. The charge is all here, right? The charge is all here. If I said, what force would a proton feel right here based on the electric field, how would you figure that out?
Would it become the top one?
Yeah, you go up here. What would you do? So you found out E in the problem, right? E turned out to be 20 newtons per coulomb. And then I tell you that there's a proton at that random location that we labeled earlier. Now I just place a proton there. And we want to see what would happen as a force result of that.
So you multiply 20 by 1.6 times 10 to the negative 19.
Yeah, if you wanted to find the force, you don't need to go to this formula, people. Look, this formula means you need to plug in everything over again. You have to redo all this calculation you did. If you find E ever, make it easier on yourself. Use that E here. Bring the Q0 up. What is Q0?
1.
The test charge you use. So if I give you and tell you, Mike, there's a proton there, or Phil, there's an electron right there at that location, that is the test charge. You are putting that charge there to test the strength of the field, really. That's why it's called a test charge. So you put a proton there. If you know the electric field, you can predict how much force that field will push on it. So ready? Here's a positive source. Here's a positive source. I randomly put a proton here. Is it going to want to move toward the source or away? Why away?
It's the same repel.
Yeah, same signs repel. Positive source with a proton, which is positive, placed here in space, would cause it to repel that way. and you would find the force of repulsion. Had it been an electron instead, it would be the force of attraction. So if you put an electron here, take a look everybody up here. The electric field produced by a positive source is indeed positive. But if you have a positive E value and you put an electron here as a negative value, you end up getting a negative answer. And remember, when we looked at attraction or repulsion between just two particles, if it was negative, they attracted. If it was positive, they repelled. As opposed to when we have three particles in line, where we did in 17.2. Okay? We'll take a look at one of those examples at some point here. When would you use this formula again?
When you're finding, like, if it's like three particles are a certain distance away, find the charge of one from the other.
Force.
The force of one from the other.
Yeah, find the force on one from the others. Or, even if it said, find the force that exists between a proton and electron at a given distance. Q1 is proton, Q2 is electron, R is the given distance. Okay? Now, the formula in the upper left corner, when you're looking for your force, you might also be looking for the distance if you're given the force. What about those multiple choice problems where I say, the distance has doubled. What happened to the force as a result? Well, if you double this, it really decreases by a factor of 4, because it's 2 squared. If I tripled this, it decreases by a factor of 9, because it's 3 squared. If I were to say what fraction of the force is a new force if you triple the distance, well, tripling the distance, again, reduces it by a factor of 9. So what fraction of the original force would it be? It would be 1/9 of that force. Okay, just like the stuff we've done this year, but applying it to these different formulas as well.
Yeah, that last part is...
So if I triple this, right?
Yeah.
It makes this denominator 9r squared. So in the end, it's the exact same equation, but you really have a 9 down here. Well, doesn't that mean really there's a 1 up here and a 9 down here, making it 1/9 of the original force? So if it says what fraction of the original is the new force, it's 1/9 of it, which is the same thing as saying it decreases by a factor of 9. So either wording is acceptable, but if it's a multiple choice, you need to be able to answer either way. It could be worded either way. Okay? All right. Next. Let's look at potential energy in the bottom right, please, before we get to the example with 3 of these particles. This was very confusing to a lot of people. And this was the video, I think. Was this the video? No, the video you watched was electric field. This was the one we did in class in 18.1. Let me reiterate something that was a little bit misleading, I think, when I explained it in class. Potential energy is a relative term. It's a relative term. It's a relative term. It all matters upon your reference point. If I were a pen and I were here and I said, what is the potential energy? The formula is clearly mgy. But what is y in this case? But what is it?
The table.
To the table?
Yeah.
Why?
Because you're over the table.
I was actually over the ground.
Oh, then it's to the ground.
Oh, but now it's over the table?
Yeah.
And now it's the ground?
Wait,
Yeah.
what?
So, remember when you calculated potential energy, you needed the height, mgy? It depended on what the ground level was considered, right? So, to answer the question is really, there's no real answer right away until you know what your reference point is. It's all relative. So if I consider this table to be ground level, then the height is about 1 meter. If I consider the ground to be ground level, then the height is about 2 meters. If I consider the sidewalk to be ground level, then we're looking at like a 50-meter drop, right? So it's always relative to a reference point. Okay, keep that in mind. Now, let's look at a quick diagram of this, what I'm saying, with electric potential energy. Here's some charge. Let's say it's negative 7e. So there's 7 electrons in space clumped together. And over here there's a helium nucleus. Helium is number 2 on the elemental table. So it's 2e. It's a nucleus only, so there's only protons. If you said it's a helium atom, it would make sense. Because a helium atom is what? Is it positive? Is it negative? It is neutral. A normal helium atom is 2 protons, 2 electrons. It's neutral. But a helium nucleus is just the 2 protons and the neutrons. The neutrons have no effect, so it's positive. Now, When you want the potential energy, it's usually with respect to the source with electric fields. What would be the source in this problem? Which is bigger? Which is a larger charge? Yeah, clearly. 7 times E is bigger than 2 times E. So clearly this is a larger charge. Agreed?
Yeah.
Please agree with me. I mean, if you don't, tell me, because I'm not seeing yeses. This is the most basic thing. Are we focusing? Are we doing things on iPads we shouldn't be doing? Let's see some nods, please. Okay, 7 is clearly bigger than 2. So this is the bigger charge here. They're both multiplied by the same constant E. It happens to be negative, but in magnitude, right, its strength is larger. So this charge is really the source, in a sense, here. Now, if you wanted to find the potential energy between them, what you're really doing is you're finding the potential energy of this helium nucleus with respect to ground level. This is ground level right here. This is the helium nucleus. Therefore, this is our R value. So it's always relative to a source. That's why the formula up here has an R in it. R is the distance away from that source. Okay? The relative value compared to that source. I'm going to leave it like that for now. The other thing I want to look at is the fact that you could be given this single diagram and asked all 3 of those problems we just looked at. So we just looked at electric force, electric field intensity, and potential energy in electric charges. All 3 of those problems can be asked from that diagram right there. Okay, the only thing you would need to know is the distance between them. So let's say we knew the distance was 12 centimeters. Well, you could find FE by doing Kc, and I'm going to point, so look at the board. Kc times Q1 times Q2 over 0.12 meters squared. That's Fe. Agreed? Next, you can find the potential energy that exists between them by doing Kc times Q1 times Q2 over just R, right? Not R squared, just R, which is 0.12. That would be the potential energy between them. Then you could find, technically, and this would be difficult, but you did in your homework, you could find the electric field produced at a given location. You need to be given that now, though. So let's say the location was right here. And we're told that this is 3 centimeters and this is 9 centimeters. So what you would have to do is use this formula up here in the top right. Kc is given. Q is this or this. You pick one or the other. You have to do it twice. So first you find the electric field produced by this negative source by doing Kc times negative 7e over R squared over 0.09 squared. Then you find the electric field produced by the positive charge. You say Kc times 2e over 0.03 squared. That will give you a negative field from this one, a positive field from this one, and then you add those 2 together using superposition. Okay? The principle is called superposition, but simply add them together to find the overall field at that location. At that location. That's the key. You need to be given the location, because you need to know what this R value is to plug it in here to find out the field from this one. Then you need this R value to plug it in here to find out the field from this one. This is the Q when you use this R. This is the Q when you use this R. You find both of those E values, negative, positive, add them up. Okay? Maria. Camila.
I don't understand why you use R squared sometimes. Like, why would you not use R squared when you're using cross?
Well, we derived it in class to know where you use R versus R squared. This is R squared clearly. Electric force is R squared, but potential energy is simply R. And we came up with that because it was QED, and we replaced capital E with KCQ over R squared, which cancels one of those D's, and you get just R. But I went over in class, so just look. Okay, look at the notes from 18.1 to see that.
This might be a stupid question.
Yeah.
To get negative 7e to a charge, do you multiply it by 1.6 or divide it by 1?
Multiply it.
Multiply it.
This is saying there are 7 electrons, and the charge per electron is that number, right? So if I said I had 7 quarters and I want to know the value, you would multiply 7 times a quarter to get $1.75. So think about it that way. You have 7 baseballs. Each baseball weighs 15 ounces. You have 75 ounces worth of baseballs, right? So think about it as a unit value always. Okay, E is the weight, not the weight, I shouldn't say, the charge per electron or proton. Let's look at some other conceptual things before we get to the examples. We'll do maybe an example mathematically of one of these. Conceptually, from this section, before we get to 19.1 and 19.2. What are the things you should know? What about field lines should you know? You open a new slide. Absolutely, that's the first thing to think about. And if anybody's curious about that, talk to Reese. I gave him an analogy this morning about contours. You could explain that to others. You're welcome to. Okay? So there's a positive source here. We know that from positive sources, the field always acts outward. How do we remember which way the field acts? Anybody know? What did I say in class? Assume that you're testing this with a proton always. Assume you take a proton or a positive point and put it in space. Which way would the proton move? Generally, though, compared to the center, would it move toward or away? Away, right? So the arrows are drawn away. Follow what I'm saying? Think about your test charge as a positive charge. It was adopted, meaning somebody decided one day to say, let's draw field charges, assuming that there's always a positive test point. Because it wouldn't make sense if you didn't make that assumption. Because then things would switch and it doesn't make any sense. You would know, was it in, is it out? It doesn't matter. Okay, depending on if it's negative or positive. So we know that it's outward. Then Scott went ahead and told us, the more lines, the stronger it is. That is a relative statement, right? I don't know by looking at this what the charge is. I do know, though, that this source that I'm drawing right now is stronger than the source that was just up there. And this source is even stronger, etc., etc., etc. And notice I'm not trying to make them overlap because field lines do not cross. Okay? And that comes back to contours, the thing that I mentioned to you this morning. The field lines do not cross. Negative fields or negative sources have the field lines coming toward them. So let's draw another negative one over here now. Let's draw negative lines coming toward them, or field lines coming toward it. Now, if these two charges are close enough, the field lines connect, and that's what you saw in that example. If 2 points in space are so far apart that their fields don't even overlap at that distance, then there's no interaction. But if they're quite close, what you'll notice is that the positive lines exiting the positive charge literally merge with these lines. They merge with them. That's what you see. And that's why you saw this in your notes when we looked at this section. When you guys, I remember I was out, you watched the video on this section. You looked at the field lines produced. That's the reason those field lines look that way. They went from positive over to negative.
So they become negative?
They don't become negatives, but the direction of the field is that direction, meaning it pushes things that way. It pushes positive charges in that direction. Okay? And think about it. Throw a proton in the middle. Which way is it going to go? A proton. Towards the negative. Take a look at the arrows. They're drawn towards the negative. It's always which way would a proton go with electric fields. They do. They loop around, but I'm just not going crazy right now. I mean, eventually some of them come off like this. Okay? What about 2 positive or 2 negative charges? What would that look like? Negatives both come inward, right? But the problem is that negative charges come from infinity. They don't come from each other. So what you would have here would be all these coming from infinity or coming from some given point or given location. And then in the middle it would be a little bit messy. It would look like this. Okay, because those field lines are going to repel each other. So those field lines, again, are not going to cross there. They're going to repel each other. If it were 2 positives, they would go outward in the exact same way, though. Exact same, literally exact same diagram, but the arrows would all be pointing outward instead of inward. All right, what else? What else? Let's jump to 19.1 and 19.2 to talk about current and resistance. What can you tell me about current? How can you describe current? A. Amps. So current is measured in amps, good. Units of A. Resistance is measured in ohms, units of omega.
It's a rate.
Okay.
Current is a rate.
Current is a rate, very good. Current is defined as delta Q over delta T. So it is a rate of change. It's the amount of charge passing a given cross-section or location in a given time period. The amount of coulombs, or the amount of charge passing a given location in a given time period. What do we make the analogy? What's an easy analogy to make for current? Water flowing through a?
Dam.
Damn.
That's better for resistance, but for current specifically, we talked about like a pipe. Think about a pipe.
Oh, right, yeah.
Because the electrons are going through a cylindrical metal wire, and a cylindrical metal wire, like a copper wire, is really a pipe, right? It's a pipe. That's all it is. There's no open inside in it. But electrons find a way through there, obviously, right? Because of their size. So when it comes to current, remember, here's what we're thinking of. This is the analogy I didn't go over in this class. So let me pause for a second and reiterate this, because the other class I went over this. Here's the way you can think about electrons moving through a circuit. Ready? Suddenly a signal is sent, and that signal says, electric field, get things going. But the electrons don't actually move at the speed of light. Although that light turned on instantly, didn't it? The electric field produced is moving at the speed of light. And that electric field is like the captain in an army. So the army's all lined up, right? They're ready to go to war, and they're waiting their, whatever spear and their sword or whatever, rifle. And he says, like, forward march. And all the soldiers start marching all at once, right? There's no real hesitation. They all hear the command and they march in tandem. And if you've ever seen an army move, it's like right, left. Like they all call out the right, every right, so that they're all moving synchronously. Synchronously? Is that a word? Can I use that word?
Shooter.
In sync.
You made it a word.
I didn't want to use in sync. They move in sync. So all of the soldiers, right, are moving. Are they moving fast? No, they're not. But a lot of them are moving on the front line, right? The front line is usually the guys who are in the front that are willing to like die in the beginning of the war. To be honest, let's be honest. So the guys in the front line are moving, and the whole front line is moving together. They're moving relatively slowly, but there's a lot of them moving together. So there's a lot of Q, a lot of charge, or a lot of electrons, but they're moving really slowly, just like the electrons. When I turn this light on, the electric field says, "Hey, electrons, start moving," and all the electrons they become disattached from their valence state. So it's a copper wire. Okay, so the electrons can easily be removed from that copper atom. And those electrons start moving from atom to atom. They keep moving over and over. And they keep progressing through this circuit at a very slow rate at the drift velocity that we mentioned. That's what drift velocity is. It's because these electrons are moving so slow. They're having all those collisions. Now, even though they're moving slow in velocity, the current can still be very large if there's a lot of them moving. Think about it. Ready? If I have a cross-section of a wire, there could be trillions of electrons literally sitting there, about to cross over that cross-section. Because electrons are so small, right? There could be many of them sitting there on the cross-section. So here's my pipe, right? Here's the electrons. The electrons are moving down the pipe. They're moving, and they're flowing through here. If there are a lot of them moving across a given location at a time, it's a very high current. Although they're moving slowly. It's a bit counterintuitive. Think about another analogy. This is what I read online when I was trying to research to come up with an easier way to explain it to you guys. Imagine a race, and there's turtles all lined up at the starting line. And the race is a length of 1 meter. It's a turtle, right? So a turtle's not going to, go very fast. So here's the race. There's the finish line right there. I see it. I'm a turtle. And I'm moving. And I'm moving. A little bit at a time, right? Until eventually, fast forward, all the turtles are pretty much at the finish line at the same time. So the first turtle gets to the finish line. While that turtle is still crossing that finish line, aren't a lot of other turtles going to probably get there also? So at the same given time, a good amount of turtles will probably be on the finish line, some part of their body, right? Their body's like this. So some part of their body is on the finish line. That's like the electrons moving over a given space or given area. A lot of electrons might be at the same location at the same time. They're moving real slow, but there's so many of them, it means that delta Q is a very large value. If you have trillions of electrons in the same location, delta Q is the amount of charge. It would be a trillion times 1.6 times, or negative 1.6 times 10 to the negative 19. So you can have a very, very, very large charge, thus resulting in a very large current, even though the electrons are moving really slow. So we think of it as flow, but think of it really as flow of charge. How much charge is really moving, not how fast are the electrons moving. Two different things. Again, electrons move slowly through a circuit. It's like a meter every hour, something like that. It's something ridiculously slow relative to think about. I mean, a meter, right? Here's a meter. It takes electrons an hour to go that far. You would never think that because the speed of light is so fast and the circuit you think is moving so quickly. Well, it's a very different thing. Again, the signal being sent is saying to all those electrons, start moving. Let's progress down the line. And eventually those electrons keep moving and they complete that circuit. So it takes them forever to get around, but at any given point in time, the electrons are outside of those copper atoms because they're all charged. There's a potential difference applied. The minute there's a potential difference applied, some sort of energy source with a positive and negative terminal, it creates a potential in the circuit, which causes those electrons to get excited and say, oh, let's go, let's keep moving. And they move from atom to atom. Okay? Elliot?
So like, the only reason the light turns on is when the circuit's completed. So like the electrons are already in there.
Electrons are already in there. They're in a stable state right now. And then suddenly we turn this on, which introduces an electric field in there, which gets the electrons going crazy. They're like, what's this field? I got to get away from it. And then it moves this way and it starts pushing this way. So then you eventually see the filament converting that electrical energy from the battery into light energy or into some other form of energy.
So like, what if I had like a copper wire with no charge? I like hooked up to like a light bulb and then I plugged it in. Why does it take a long time? Because it takes a long time to get electrons all the way through.
The electrons are in the light bulb. They're there already. The filament in the light bulb is made of some sort of metal. That's what happens. This is an old school light bulb. The new incandescent ones has to do with gas, right? So imagine you have the filament. In that filament, there already are electrons in there. So as soon as you hit the light switch, the electrons in the filament, they get excited also. They all get excited right away because the signal is sent to them at the speed of light. They're not moving that fast though, but it gets to them that quick.
So is the signal like it's sent along the copper wire also?
Yeah, the electromagnetic field, the signal, that's what's moving along there.
Okay.
And it's causing those electrons to get excited, and then there's a reaction. The reaction between the electrons and whatever's in the bulb that produces light. It's not just like, they're excited, so there's light. There is a reaction, some sort of chemical reaction that goes on to produce light as a byproduct. That's why a lot of the time for like, what was it? I think somebody brought it up in this class. Neon light signs and stuff that have gases in them. When you break them, the gas it no longer works because the gas has to be in a fixed pressure. So the gas comes out to be a certain color based on different excitations of electrons. That's what's happening. We'll learn more about that when we get to nuclear physics toward the end of the year with the different colors of neon lights, how they're produced and stuff. But the idea there, you don't have that gas there, so no longer can that reaction occur. So even though you've completed the circuit, there still is electricity flowing to that neon sign. But you're not going to see that color that you want to see because that reaction isn't occurring with the gas. Okay? Let's take a look at the second formula in 19.2 now. V equals IR. Whose law was this again? Ohm's law. Ohm's law. And we talked about ohmic and non-ohmic materials. What is the gist of that? What's the deal there, Nick?
Well, ohmic materials don't have variable resistances, but non-ohmic do have variable resistances.
Exactly. So for example, if I were to, everybody look up, double the current, it should double the voltage in a ohmic material because R is kept constant the whole time. When R, take a 3-minute break, we'll finish this up and then I'll give you time for promise. With V equals IR, if we remember, if a material is ohmic, the resistance is constant. So if we solve for R here, and we did this in class, right? We get R equals V over I. Well, if the resistance is a constant number and it's not changing, if I double the voltage, I have to double the current. If I triple the voltage, I triple the current. So Reese just showed me a quick cool video, and the guy was electrocuting himself, like as a joke, with very low voltage. And he talks about his tongue having a lower resistance than his body. So the tongue had a fixed resistance, but he had to keep lowering the voltage to lower the current. If he had too high of a voltage, the current flowing through him would be a very high value, and it was electrocuting him more. So with an ohmic material, as you increase voltage, you increase current. As you decrease voltage, you decrease the current. If the materials were non-ohmic, this would not be true. For non-ohmic materials, you may double the voltage, but the current may only go up by like 1.5. You follow what I'm saying? It's not proportional in that sense. So non-ohmic materials do not have proportional increases between their voltage and current.
That's why the value curve is changing in the graphs?
Yes. That's why the first graph was linear, showing the slope was constant. Because as V goes up, I goes up. As V goes up, I goes up. But in the other one, V goes up some, I doesn't go up as much. So you see that curved nature to the graph. Very good, Scott. Good. What else about resistance? We had 4 things that affected resistance. What are they?
Temperature.
One of them.
I just want to go like order.
Ask somebody.
Cross-sectional area.
Cross-sectional area. What else?
Length.
Length. And then finally materials, which is different. As temperature goes up, what happens to the resistance?
Goes up.
Yeah, where do you remember? How do you remember that? Think about what?
Superconductors.
Yeah, and you can think about the reverse for superconductors. How do superconductors work? Temperature goes down, resistance goes down. Computers, as it gets hotter, they get slower. There's more resistance, the idea. They slow down. Not directly correct with computers, but the idea of the analogy.
Is the subway more efficient when it's cold out?
Because they run on electricity.
It's like out the like bars are outside, like the third rail's outside.
Yeah.
Or does it really not affect it?
I don't think it affects it because the velocity of the train is only affected by the power of the engine. The power of the engine is a result of, you're going to learn in 19.3, P could equal several things. It could equal V squared over R, it could equal I squared R, it could equal I times V. But they could control the voltage and current by increasing the power. So no, it's not going to go faster or slower, but it has to work harder or less hard to go that same speed still. Yes, the amount of energy needed to run in the winter and summer is indeed different. But they'll still run at the same speed. Yeah, the amount of energy needed is different. Yeah, that's a good point. Cross-sectional area. As a pipe gets bigger, is there more or less resistance to water flowing through it? Yeah, less resistance. Okay? Think about pipes for that one. And then finally, as the length of a wire gets bigger, there's more opportunity for collisions. So stuff slows down. Okay, resistance has to go up for stuff to slow down. Think of resistance as you would think of friction. Always. Okay? Think about a superconductor. A superconductor is really just an ice skater. That's all it is. An ice skater has very little friction, right? A superconductor has almost zero friction in it. Literally almost zero resistance. Okay? And certain ones, you can get it down to the point where the resistance is negligible. You could apply a voltage to something. You can apply a voltage to a superconductor, remove the voltage, and that current will go on forever. Exception to what he was saying, though, there on a superconductor. If you want to see an application of a superconductor, I put a handout, 19-2 resistance handout under documents and handouts. And it talks about what are those called? Trains in Japan that run on magnetics. The maglev train. The maglev train uses the idea of superconductivity. Look at the article. It's really interesting. You could also look at News Forum, and earlier in the year, or last year, I put on a video called Quantum Levitation. So if you hit News Forum, and they all show up, just hit Control F, run a search for quantum levitation. There's a really cool video of a superconductive particle floating above a magnetic field, literally going on forever, and it's just floating in space. They give it a little push, and it never stops. It's analogous to the maglev train, really. Okay, but the maglev train is really controlled by the magnetic poles changing and moving. But it uses superconductivity for it to work.
We talked about those another time. I forget when it was though.
We did earlier in the year, yeah.
With the golf cart or with the?
No, with the actual train.
We mentioned it earlier. Excuse me. Finally, the material. What is about the material? And we talked about this, but we didn't really answer this question, remember? It's kind of one of those, like, there's an explanation, but not.
Well, if it's like copper, then there's less resistance, but if it's, I forgot what the other is. Iron.
Yeah, so like iron, gold, nickel, all those, they have more resistance than copper. Copper is used because it's cheaper and very little resistance. There is one element that has less resistance. Silver. Good. You saw the email?
No.
Oh, you just remember? I mentioned it? Okay. I also put in that email, yeah. Silver, although expensive, is less resistant than copper, but you wouldn't use it for that reason. Then I talked about gold-plated stuff with corrosion, right? Okay. I mentioned it. Right. So those are the 4 things that do indeed affect the resistance of a wire. Okay? Let's see if there's something else I want to talk about. We talked about batteries and generators. We talked about batteries and generators in section 19.1. What do you remember about a battery and a generator? How are they different? And what are some examples? And don't tell me a battery is an example of a battery, please.
Wasn't a generator like the dam?
A generator is like a dam. Very good. What does that convert? What kind of energy?
Flow.
It converts some type of energy into electrical energy for a generator. Mechanical, good. Because it turns a turbine. That turbine turns a magnetic field, inducing an electric charge that can then charge up some sort of a generator. Mike?
And then battery is like chemical energy into electrical energy.
Yeah. The easy example for a battery is like a salt bridge. When there's some sort of chemical differential or chemical energy stored. When chemical energy is converted to electrical, it's called a battery. That's why you have corrosion on batteries. The corrosion you get is usually partly from oxidation and partly from the chemicals themselves. Sometimes some of the chemicals seep out of the terminals. Okay? And you get that like green-white powder.
Yeah. Yum.
AC versus DC.
What a good band.
AC versus DC, not the band.
Where did you get your skinny toe?
Come on, you guys came up with that example. Elliot, Mike, and Scott came up with that example. What's the difference in AC and DC?
The
band.
One jams
It never stops coming back.
is alternating back and forth.
It's like they're
When you
vibrating.
switch.
No,
Yeah,
the
the
two
switching and
poles.
vibrating back and forth. So alternating, yeah, the poles are constantly switching, or the current is one way, then it's the other way, then it's one way, then it's the other way. So that electron is not actually moving. It's got zero net displacement because it does this, and then this, and then this, and it goes back and forth forever. So it's like a spring oscillating back and forth.
Wait, but does
Okay.
that have to do with the
The poles switching.
the faster they switch, the faster.
The faster that flickers, yep. Higher frequency, flickering of
So
lights.
then it's like, wait, if it's like that, then you can't see the flicker.
Correct. If the frequency is high enough, human eyes don't pick up on it, you can't see the flickering. If the frequency is very low, then you would see that pulsing. What else? What's a pentiometer? Pentiometer, Nick.
Device used to like vary resistance.
Exactly, it just varies resistance. Now, it can vary resistance in many ways, folks, in many ways. I could turn a dimmer and dim a light, and therefore that light bulb has to also be a variable resistor. This changes the amount of flow, but the light bulb itself also changes. The volume control on a volume knob. We talked about a joystick on a game controller. Okay, a pentiometer is a variable resistor. Think of anything that's like a dimmer, okay, anything like that at all. Any volume control source is always going to be a pentiometer. I will tell you now that you will have to do 3 math problems, and then you will choose one of 2 of the last 2. The last 2 have to do with, one of them is with the 3-point charges. The other one has to do with an electric field, and then introducing like an electron or a proton into that field, figuring out the electric field itself, then figuring out the force, where there's like a part A and part B to that. Okay? So think about those for your part 2s. The other 3 for part 2s are all pretty straightforward. Okay? They're all really straightforward. Make sure you just look for your key indicators as to what the key words are. When you see newtons, use your units. Newtons are force. Newtons per coulomb is capital E. Joules is PE. Use your units. Catherine.
How many points is this test for?
The test is 85 points. 85 points. Okay? It's your 3rd test of the quarter. It's your final test. If you're absent on Thursday, you must take it on Friday. Make sure you are here one of those 2 days, obviously. Email me. That's all right. You also email me for extended time, please. You have 2 days to do that. Okay, I'm going to stop the review here.
Wait, I have a question.
Yeah.
For the problem sets, it said 50. It was like the mu